Welcome to The Explainer. We're going to dive into a paper that really makes you question how we're building intelligent machines. It starts with a pretty provocative idea. So think about the most powerful AI you've ever interacted with. You know, the one that can write code, draft an email, maybe even create some art. Now, what if I told you that this incredible AI has a serious flaw, a kind of digital amnesia? What if it's basically trapped, unable to form new long-term memories, or really learn from its experiences with you? Well, the paper we're looking at argues that this isn't just a hypothetical. It's a real, fundamental problem with how today's large language models are designed. See, they're essentially static. Their knowledge gets frozen in time right after that huge, expensive training phase is over.
And this slide really nails the issue. The paper uses this powerful analogy. Anterograde amnesia. That's a real condition where a person can't form new memories. And that's kind of what's happening with an LLM. Its entire world is its pre-training data. That's its past. And its present is only what's in the current context window. The second that conversation ends, any new information you gave it, poof, it's gone. It's like talking to someone who completely forgets who you are the moment you walk away.
So you have to wonder, right? How do we end up with these brilliant AIs that have such a critical memory problem? Well, the answer really lies in the philosophy that has driven AI research for years, the idea that deeper is better. For decades, the thinking has been that to get smarter AI, you just add more and more layers to the neural network. Yeah, the recipe for building AI has been pretty straightforward for a while. Get a ridiculous amount of data, build a network by stacking layer upon layer, and if you want it to be better, just add more layers and make the whole thing bigger. But, and this is the core argument of the paper, this is an illusion. Sure, it's given us some incredibly powerful models, but it's a dead end if we want AI that can actually adapt and learn continuously. It's like building a skyscraper taller and taller, but never giving it the ability to change or react to the world around it. See, the thing is, just making models deeper doesn't fix the really hard problems. It doesn't solve catastrophic forgetting, which is where a model basically wipes out old knowledge when you try to teach it something new. It's like trying to teach a student a new subject by making them forget everything they've ever learned before. It's not ideal. And that's what has researchers asking, is there a better way? Do we need a whole new approach? Okay, so if just stacking layers is the illusion, then what's the reality? This is where the paper introduces a really fascinating new paradigm. It's called nested learning, and it's a totally different way of thinking about building intelligent systems. Now, to really get nested learning, we first have to kind of redefine memory and learning. The paper makes this super important distinction. A memory, in this sense, is just any change in the network caused by new data. Simple enough. But learning is the process of making those changes, those memories, actually effective and useful over the long run. It's the difference between just memorizing a random fact versus truly understanding how it connects to everything else you already know. So, what is nested learning? Instead of thinking about that one tall stack of layers, I want you to picture a set of Russian nesting dolls. Each doll represents its own learning process, running at its own speed. The big outer doll could be a really slow, deliberate learning process that happens over weeks. And the tiny innermost doll could be a super fast reactive learning process that happens in milliseconds. And that's the crucial shift in thinking right there. The goal is no longer just architectural depth, it's about adding more levels of learning. You know, this whole idea is inspired by our own brains, where different parts handle information and memory at different speeds. Our hippocampus, for example, is great for fast, in-the-moment learning, while the neocortex handles the slow consolidation that happens when we sleep. Nested learning is trying to build that same kind of multi-speed system into our AI. Now this is where it gets really interesting. The paper argues that this whole concept of nested learning isn't some brand new theory we have to invent from scratch. It's actually been hiding in plain sight this whole time, inside the tools we already use to train our models. Let's just walk through a quick example. When we trained any model, what are we doing? We're updating its main parameters, its weights, right? We'll just call them W. This is the main outer learning loop. It's a pretty slow process that happens over the entire training dataset. It's kind of like a student spending a whole semester studying a textbook. But in practice, we hardly ever just use that basic process. We use an optimizer to make things better. And a really common ingredient in those optimizers is something called momentum, which we'll call M. All momentum does is help speed up training by keeping a sort of running average of past updates. Think of a ball rolling down a hill. It picks up momentum and just goes faster and smoother. And right here, this is the big reveal. The paper points out that the momentum term is itself a secret, faster learning process nested inside the main one.
So while that slow outer loop is learning from the data, the inner momentum loop is updating with every single step, and it's learning to compress the flow of information. It's like a student who not only learns the textbook material, but also learns how to study more efficiently. It's a two-level, nested learning system we've been using for years, maybe without even realizing it. All right, so we've got the theory, and we've even seen how it's been hiding under our noses. So what happens when you take this insight and actually try to build an AI with it right from the start? Well, the paper introduces a new architecture called HOPE, designed specifically for this kind of continual learning. So, the researchers took these ideas and developed this new architecture called HOPE. It's a self-referential learning module, which is a fancy way of saying it's built to learn how to learn. The whole thing is designed from the ground up on these principles of nested learning, with all these different learning loops running at different speeds. And one of the coolest features of HOPE is what they call a continuum memory system. Take a look. You can see how different parts of the model are explicitly designed to update at different rates. You've got fast memory, which updates constantly. That's like our short-term working memory. Then you have slow and persistent memory, which update much less frequently. This mimics how our own brains consolidate knowledge into long-term storage. It lets the model learn quickly, but also lock in that knowledge for the long haul.
And this isn't just a clever idea on paper, it really works. The results show that the HOPE architecture actually outperforms a very strong baseline model, Transformer++, on a bunch of common-sense reasoning tasks. And these are tough problems that require a real understanding of the world. The data suggests that building models with these different learning levels gives you real tangible benefits in both performance and, importantly, adaptability.
So, what's the big picture here? What does this all mean? The key takeaway is that nested learning could be a huge shift in how we build AI. It's a potential path away from these static, frozen models that are trapped in the past, and a path toward AI that can learn on the fly, adapt to new things, and evolve over time, a lot more like we do.
And this new paradigm leaves us with a final, really exciting thought. If we move beyond this illusion of deep layers and really embrace these nested levels of learning, are we on the verge of creating an AI that doesn't just know things, but can actually learn and evolve right there with us? An AI that could be a true partner in discovery and creativity? The future of AI might not be about building bigger brains, but about building brains that can learn and grow.